Good evening. Welcome to the fifth and last public lecture of the year, organized by the Institute for Mathematical Sciences. My name is Tom Chita. I'm the director of the Institute. So this evening we have Professor Bruce Reznick from the University of Urbana-Champaign to give the public lecture. Professor Reznick, you have read his CV, was born in New York, Manhattan, I was in school, and then the family moved to LA, and where he entered Caltech and graduated in 1973. But when he was there, he was on the Caltech team in a Putnam mathematics competition. And I won the first, number one. The team was number one, and he was on the team. And subsequently, in the 80s, from 1983 to 85 years, involved in this Putnam committee, setting questions. Yes. And he graduated in 1973 and then went to Stanford. Previously, they got the PhD. And then, after spending 3 years as a postdoc, first at Duke and then Berkeley, he joined Illinois, Urbana-Champaign, in 1979, but he has been there ever since. Now, Professor Reznick has a very colorful mathematical life, as I read from the CV. Among other things, he has supervised more than 100 undergraduate research projects. I'm not aware of anyone, at least in this department, in Singapore, who has done as much in terms of supervising undergraduate students. And he was also a Sloan Fellow, has been a Sloan Fellow, and was a member, a fellow of the American Mathematical Society. That was he was elected in 2012. It was the first time that IMS instituted this fellowship. Professor Reznick is an outstanding teacher. He received a University on Campus Teaching Award for excellence in teaching in 2009 from the University of Illinois. So we are very happy that he's able to give us the public lecture this evening. The title is A Walk Down Arithmetic and Geometric Mean Streets in Mathematics. Please welcome Professor.
Thank you very much for coming. I do want to mention before I start that there are more than 100 undergraduate and graduate students from Singapore who are at my home university in Urbana-Champaign. They are currently taking final exams. There were 8 inches of snow on the ground last weekend, and it's minus 6 degrees centigrade. I checked before I came here right now. So please send them your warm thoughts. I do want to thank the Institute for Mathematical Sciences and the National University of Singapore for their great hospitality, for their kindness in inviting me both to come to this conference and to give this talk. I also want to very specifically thank Ms. Eileen Tan and Nerleen Binti Muhammad of the staff who've done a really incredible job. I've been to a lot of conferences over the years in many places, and I've never been anywhere where the local information was presented more better than here. We're coming from far away. I looked it up, and Urbana is 38% of the circumference of the Earth away from here. And to be able to have that happen and to feel even partially at home is quite an accomplishment, so I want to thank them for that. So I have to do some math. This talk will be about 2 kinds of averages and a relationship between the two, and some seemingly advanced problems that you can actually solve easily once you know the relationship between the 2 averages. Now I want to start, I know that there are a lot of people from the conference here, but there's some people who aren't, some people who might be even a little younger than the average conference participant. So I'd like to tell you that in this talk, letters at the end of the alphabet will mean real numbers, and my real numbers are always going to be positive or zero. It's W, X, Y, and Z. If I don't want to say how many numbers I'm using, I'll use subscripts, X1, X2 through Xn. And some people really don't like algebra. And this is a legitimate issue, and I want to make a slight defense. Think of letters in algebra as pronouns. X is she, Y is he. You have no trouble, at least in English, in using a pronoun where he in one sentence will easily be different from he in another sentence. So don't be upset if X is 3 once and then X is 7. And it's just easier to say X squared plus 7y than the first number squared plus 7 times the second number. So we do this to save time. The first average I want to talk about is called the arithmetic mean, and I'll always write it as capital A. The idea is if you have n numbers which are positive or 0, you imagine that there would be some number that if you added it to itself n times, you would get the same thing as the sum of the numbers that was given. And if you play around with this a little bit, you get an algebraic expression. And for those of you who aren't comfortable with algebra, just accept that this is the same thing as that. It just is a little shorter. This is the usual average you've seen working with data or dollars or calculating grades in a class. Now, there are a lot of teachers in here, so I have to mention things like that. The second average is called the geometric mean, and I'll always refer to it as G. And here, I'm going to write times for a little while, but I'm not going to write this too much longer. Again, if you imagine a product of things equaling the product of the numbers you get, then you get an expression. Here, I usually like to not write times just to make it shorter. And this is an expression for the nth root of the product x1 through xn. This average is less common. The most common use that I could find of it is if you want to find the average rate of return of an investment over a certain number of years, you take the total growth and then take the root that you're dividing it by, and then your growth in your investment would be as if you grew by G every year. Now, one of the things that's either bad or good about the geometric mean is that 1 0 can mess everything up. If you have an arithmetic mean of a large number of objects, one value isn't going to change it very much, but 1 0 is going to spoil the fun for everybody. And the financial version of that is that if you lose all your money 1 year, it doesn't matter how much you made before, you still lost all your money. And now I want to tell you about people, not so much in academia, but in when you see magazine articles about giving a talk or a presentation, they say you should always make sure that there's one idea that everybody gets out of the talk if they don't remember anything else. And this idea is that no matter how I choose these numbers, and no matter how many I take, the arithmetic mean is always at least as big as the geometric. And a second part that's almost equally important is that if these things happen to be equal, then you know you started out with things that were equal. And the problems that I'm going to tell you that are given in a calculus class that can be solved without calculus are going to be using this. So this is called the inequality of the arithmetic and geometric means, or the arithmetic geometric inequality, or the AGI. The topic of solving these problems is more generally called mathematical optimization. If you find this interesting, Google mathematical optimization and you will find many things. Much more information than I can give you in just a minute. And now I want to just, again, remind you of some of the rules of exponents. X to the A times X to the B is X to the A plus B. X to the A to the B power is A times B. Now, this doesn't look very exciting, but one of the topics in our conference is something called tropical geometry. And in tropical geometry, multiplication becomes addition and exponents become multiplication. I won't tell you what becomes addition, but that's something else. Go to our conference and find out. Now, the arithmetic-geometric inequality in one line, and mathematicians love to write things in a very terse way, would be in this form. This is the arithmetic mean, the geometric mean. And if we multiply it by n, we get rid of fractions, which makes people feel a little more comfortable when we get to here. I should explain this. In the US, I'm known for enjoying Asian food. And if you go to an Asian restaurant in the US, whether it's Indian or Chinese or Japanese or Thai, an item on the menu that is relatively spicy will come with one of these little chili peppers. And the more chili peppers you have, the hotter the object is. And I thought I would give you as a guide in this talk to the level of mathematical or algebraic difficulty, the number of chili peppers you see per year. Just so if you find yourself lost, you might think that it's because of math. So here the idea that I want to do, if you remember what I said before, was the arithmetic-geometric inequality. I want to write xi as yi to the n, where yi is the nth root of xi. Now, we do this as mathematicians because we can and because it works. There's no, it's not an obligation, it's just a simplicity. And the reason for doing this is that if you make the substitution, then the arithmetic-geometric inequality has a very nice form. There's no roots, there are no fractions, it's nice and simple. So if you believe what I said, I hope you do, when n is 2, the arithmetic-geometric inequality is simply this expression. And this is the expression of when the two sides are equal. I want to prove that this is true. Those of you who are good at algebra can probably see this coming next. I take the 2y1 and y2 over to the other side and notice that I have a square. The last statement is true because squares are non-negative. A positive number times a positive number is positive. A negative number times a negative number is positive. I'm not talking about complex numbers here for the wise guys in the audience. I'm talking about real numbers here. And as simple as it sounds, much of my research and the research of many people at this conference is based on the fact that squares can be negative, and if you add up a bunch of squares, it can't be negative either. So what we've done here is shown that this is true and this is true. And if we translate back by letting y1 be x and y2 be y, we get the form of the arithmetic-geometric inequality when n is equal to 2. Proofs are important to mathematicians. I think if you ever asked a mathematician, you would get that out of them. And this is a very important thing to say. Mathematical statements, such as the ones that I'm giving today, are not true because I'm a big shot professor and I say that they're true. Because I'm not, and it's not just that I'm not such a big shot professor anyway. Statements are true because we can formulate a proof that follows the accepted rules. Mathematicians will forgive mistakes, mathematical mistakes that we make, but we don't really forgive people who will make an intentionally incorrect argument for some purpose. And this final point for the students here, proofs were not invented to torture students. They are a necessary part of the subject. Another thing that's worthwhile to know is that mathematical truth, unlike statements perhaps in the humanities or social sciences, are universally true. 1 + 1 is true for boys and for girls. It's true in North Korea. It's true in North Carolina. If there's intelligent life in space, then 1 + 1 equals 2 there, provided we know how to translate it into the appropriate language. And one other thing to note is that the correctness of the logic matters but a proof may not seem to make sense at the beginning. People will write a mathematical proof and they'll start with assertions and you're saying, what's going on here? It doesn't seem like it has anything to do with what they're trying to prove. But you just have to keep your eye on what's really going on. We never have to explain how we find proof as long as the proof is true. So now I'm going to give you a proof. And this might be a little risky, but I'm going to give a couple of proofs. And you perhaps saw this picture or an earlier version of this picture in the poster. This was, in case you're interested, I made this in Mathematica. I'm not a particularly good graphic artist, but Mathematica knows how to do math things. So before I tell you what the lengths involved are here, I have a line from A to C, a straight line that's broken up with B. The midpoint of AC is E. I then draw the circle whose center is E passing through A and C. At B, I put up a perpendicular and connect it to form the right triangle with right angle at D. And then, because it's a little less interesting, I draw two radii, the radius from D to E and the radius from E to F. And I'm going to use this to prove the arithmetic-geometric inequality for n is equal to 2. And this is the original proof. So this is the same picture I had earlier. I thank LaTeX for its ability to scale pictures very easily. So here's what I do. I let x be AB and y be BC, and then I draw these line segments, and I'll assume that x is bigger than 1. As I said, I construct the midpoint of this line segment, draw the circle, and construct perpendiculars. Now, EF is a radius, so its length is half the length of the diameter, and that's conveniently x plus 1 over 2. Now, BD is the side of a right triangle, so this length at BD is less than the hypotenuse ED, but ED is a radius of the circle, so its length is the same as this radius, which is x plus 1 over 2. And the only thing I have to do now is calculate what BD is. And then I'll complete the calculation. So, here's the part that I probably should have put a second shell in here. It's a fact from Euclidean geometry that this triangle and this triangle are similar. That is to say, they have the same shape. The reason is that this angle plus this angle is 90, and this angle plus this angle is 90, so this angle is this angle. That's right. And what that means is that the ratio of this side to this side is the ratio of this side to this side. And the algebra of that tells us that BD is actually the square root of xy. And the square root of xy, because it's a side, is less than the radius, which is x plus y over 2. Now, why would Euclid have wanted to do this proof rather than the one I gave earlier? Well, they didn't have algebra. They had to do all sorts of things that they didn't have algebra for. Very impressive. So let me start by giving you an example of the sort of problem that can be solved by AGI. Suppose you want to find the proportions of a rectangle with a fixed perimeter that has the largest area. So let's say the rectangle has height x and width y. The perimeter is 2x plus 2y, and the area is x times y. Let's take some examples. If x is 1 and y is 5, you get area 5. X is 2 and y is 4, area 8. X 3, y 3, area 9. Now, this is what the AGI tells us. And what we want to do is we want to, the technical term is massage the information that we are given so that we can use the formula that will help us. The perimeter is 2x plus 2y. So x plus y over 2 is actually 1/4 of the perimeter. And this expression says that 1/4 times the perimeter is bigger than or equal to the square root of the area. And if I take the 4, sorry, if I take the 4 over to the other side, the perimeter is bigger than or equal to 4 times that. You can read this. Square it and get this. The important thing here is that the perimeter gives an upper bound for the area, and the area gives a lower bound for the perimeter. So given the data that's given, the arithmetic-geometric inequality tells us that the area is at most 9. And the only way to do it is to get x equal to y. And if you figure that out, that's x equals y equals 3. The same problem, the same algebra solves a different problem. If you have a rectangle with a fixed area, what's the smallest perimeter? The same argument will tell you the smallest value of the perimeter comes when x is equal to y. Is this okay with everybody? Or I shouldn't say that. I should say, is there anybody for whom this is not okay? Now, one other thing that students often ask, it's not in the textbook, and it's a very good question. What's the largest perimeter you can have for a rectangle of a given area? And the answer is forget it. There is no largest perimeter, because you can just make a really long and skinny rectangle. The perimeter can get as large as you like, and you'll be fine. But that's better. Now, I stole this one from the web. I realized when I decided to give this talk, that at some point I would have to learn how to put pictures into Beamer. So I looked for a picture of this situation, which is an extremely common calculus problem. A farmer wants to build, in this case it's a garden, usually it's fenced-in material for the animals, and he wants to use the side of a barn. So the garden is W by L, but you don't have to buy fins for this part of the barn. So again, you can look at this and write things down. The perimeter is 2W plus L. You don't count that because you don't have to buy the fence in the perimeter. And then the arithmetic-geometric inequality, as before, says the perimeter over 2 is 2W plus L over 2. The square root of 2 times the area. Again, the perimeter is bounding the area with slightly different numbers, but what's relevant here is the maximum value. The maximum area occurs when 2W is equal to L, and that sort of makes sense because it's cheaper to make it wide than, it's cheaper to make it long than to make it wide because you only have to pay for it once. Now, I'd like to tell a story about Illinois. You may think of Illinois in terms of Chicago, which is a very, very big city, but most of the state is agricultural. And at the University of Illinois, we often get students who grew up on farms. Knowing that in my first year when I was teaching the calculus class, since an example like this was in the textbook, I thought I would do an example of the board of a variation of a farmer who wants to build a pen for his pigs with one side running along the river. And the mathematics was completely correct. And after I did the problem, one of my students raised her hand and said, "Professor Reznick, do you know that pigs can swim?" At that, now I did. Didn't use that example. Okay. Now we're up to a couple of things. Now here, for those of you who really don't like algebra, just sort of hum along with what I'm doing here. If you happen to take these 3 squares and expand them out and rearrange them, you get this. This is a sum of squares, and this is always greater than or equal to 0, so this expression is greater than or equal to 0. Now, the only time it would be equal to 0 would be if each of these were 0, and that only happens when x is equal to y is equal to 0. Now, it just happens to be an algebraic fact that if you take this polynomial and multiply it by x plus y plus z, you get x cubed plus y cubed plus z cubed minus 3xyz. You should check the algebra for homework. You weren't expecting homework, were you? Excellent. So what's the significance of this? On the last page I showed you that this expression gives you the AGI for n equals 3. I'm going to give you another proof of the AGI for n equals 3, but first I'm going to give the AGI for n is equal to 4, and notice that we're still in the 2 chilling category here. So this is the statement of the AGI for n is equal to 4 with 4 variables. And I'm just going to do some algebra tricks. There's no other way to say it but this. The first thing I want to do is I want to write the left-hand side as the average of x plus y over 2nz plus w over 2. Then I'm going to use the Arithmetic-Geometric inequality there and there to move it to there and say, oh look, I can use the Arithmetic-Geometric inequality again and get this. And then you have to forth through of x, y, and w. Now remember what I said about proofs. This is a completely unmotivated proof. There's no a priori reason why you have to do it, but it works. And because it works, and each step can be justified, this is a valid proof. And this proves the Arithmetic-Geometric inequality for n is equal to 4. Now you can always do this to go from n numbers to 2n numbers, but 2n is even, so you want the inequality for odd. There's one more computational technique that lets you go from n to n minus 1. And I'm only going to show it here when n is equal to 4 because I like you and I don't want to make many of you unhappy. So here's the thing. You take this equation, which we now know is true by the previous slide, and I want to let w be the cube root of x, y, z. Why? Because it's going to work. This is part of the reality of doing things in doing algebraic methods in math. There's a great proof from Polian and Zago, who are two wonderful mathematicians in the middle 20th century, which is a trick is just a technique you've only used once. So this is, at this point it's a trick, but eventually it becomes a technique. What do I want to do is, well, let's look at the right-hand side first. If I put in w equals x, y, z to the 1/3 and do a little bit of the algebra, I'll notice that it just disappears. The geometric mean of x, y, and z and the geometric mean of x, y, and z is equal to the geometric mean of x, y, and z. You can tell why I use algebra rather than words for that. Now let's see what happens to the left-hand side. The left-hand side, I put in the value for w, so that becomes this expression, and then I have this is bigger than what I have on the right-hand side, and then I'll subtract the second term from both sides. And now I'll multiply it by 4/3. And with this trick, I go from 4 to 3. This goes from 2n to 2n minus 1. And I have to tell you that we love this kind of calculation. If we can find one of these things, it makes us happy along the way. So again, as I say, I will tell my friends in the audience, mathematicians in the audience, that this is actually enough to prove the general statement by induction. Now, induction, I don't want to go into here, is usually much more directly. You go from 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8 to 9 to 10 and go up the ladder of mathematical truth. Here you jump up, come down, jump up, come down, jump up, come down. But eventually you get as high as you need to be. Let's do some more problems. If you have a rectangular box with sides x, y, and z and a fixed surface area, how can you maximize the volume? Well, the sides have areas x, y, x, and y, z, the various sides of the box. Each one occurs twice. That's the surface area, that's the volume. Here's what you do. You just plug them in and hope something good is going to happen, and something good happens. The surface area over 3 is this, Arithmetic-Geometric inequality, algebraic shake and bake, and that becomes twice the volume to the 2/3 power. Once again, the surface area bounds the volume in this way. And the maximum value occurs when 2xy, 2xe, 2yz are equal. Not very interesting, actually, and totally predictable. Now, we also often ask the question, what happens if you have an open box, so you don't have to pay for the lid? Here, the surface area becomes just xy, 2xe, 2xy. The volume isn't changed, and the same sort of calculation works, and we're pretty happy. The maximum now occurs when these things are equal, which turns out to be this. And what happens here is that x and y are bigger than z. You have a box that's bigger because you don't mind having to pay for a lid that only counts for half. In calculus classes, we often make up problems where the tops and the sides are made of materials of different cost. I assume this is true here as it is in the US. And you wind up with something like axy plus bxc plus cyz. And you do exactly the same thing to try to find the maximum. And my point here is that you don't need calculus. You can do it with calculus, but you don't need calculus. Now, I thought when I was coming to Singapore that owing to the reputation of the city in world financial markets, I ought to have one financial example. I am not Warren Buffett, so my example won't be particularly fancy. Let's suppose you're offered two stocks. One goes up 5% a year for 5 years. The other one, they say, well, it doesn't do much the first 2 years, but then it'll go up 5 and 5, and then it'll really go up the last year. And the question is, which one is better? And you might be told by the salesman, well, the average is 5%, so it's the same thing. Well, you can do the calculation. But first of all, just remind you that going up by I% is multiplying the total by 1 plus I over 100. So if you started at $100, in the first case, you'd wind up, I did this on Mathematica, I didn't calculate it myself, $127.63. The second case, if you work it out, is $126.79. You get about $1 less. It's not a huge difference, but people make their fortunes from small differences like that. And I want to analyze this a little more. In the first case, if you want to figure out what your true growth rate is, that would be whatever number you would multiply this by so you had the same growth every year and wound up with that amount of money. And it turns out to be 4.86%. That's less than 5%. The Arithmetic-Geometric inequality says the true average rate of growth is never bigger than the average of the yearly growth percentages and only equal when the growth is the same every year, which is in words, this is in symbols, this is the average growth, this is the arithmetic-geometric inequality, this is a little bit of algebraic manipulation. This is the average rate of growth arithmetically. And this is what I set up there. Okay. Now, the last geometric example I want to give is one that's going to look a little strange, because I'm going to do something completely unjustified that works. And even though it's completely unjustified and works, anybody here who has had a high school science class will recognize the underlying problem that I'm working with. So let's say you have a can of Coke, or I don't see any cans here, just these bottles, but you can imagine a can, right? The can has radius r and height h. Its volume is the size of the lid, which is pi r squared times h, and that's the volume. What about the surface area? The surface area, you have a top and a bottom that are each pi r squared. And then if you think of a can, unroll the can, and you actually have a rectangle whose height is h, and whose width is the circumference of the can, and you have 2 pi r times h. So here's what you want to do. You take the surface area, 2 pi r squared plus 2 pi r h, divide by 2, and that's greater than or equal to the geometric mean of these two. And if you work it out, you've got the square root of r cubed h. Now that's correct. But it's not really too helpful, is it? Because it's not a function of the volume, because it's got an r cubed h rather than r squared h. And it turns out that what you want to do is you want to break up one of the sum ends into 2 pieces here. Again, this is something you do strictly from desperation if you're a student, because there's no natural way, unless you've seen the method, that this is what you want to do. And again, we do it because it works. So here's what I do. I break it up into pi rh plus pi rh. It's still 2 pi rh. I haven't changed the numerator. I haven't changed the left-hand side. The right-hand side, when I multiply everything out, I get a whole bunch of pi's and r's and h's, but I've got r squared h here. R squared h is the volume of the pi, and then I have something that does work. Now, the first comment is the optimal value occurs when 2 pi r squared is pi r h is equal to pi r h. Well, this part isn't so interesting, but you get h equals 2r. If you want to minimize the surface area of a can, you want to make the height of the can equal to the diameter. Now, maybe that works for tomato sauce or for other sauces, but that doesn't work for Coke. And my guess is that the top and the bottom might actually be more expensive than the sides. You want to be concerned about the welding and the connection. You don't like having the lids blow up very much. But how did I know to take this once and this twice? Well, chemistry. Forget about the constants. Look about r squared and rh. If you were given in your high school chemistry class, and I hope they're still doing this, if you were told to balance an equation, some combination of R2 and some combination of RH equals R2H, it would work out to be 1, 2, and 2. And those are exactly what shows up here. You take the pi r squared once, pi RH twice, and you wind up getting 2 copies of the product of the volume. Now, to really balance chemical equations involves linear algebra, which is a subject I know is dear to the hearts of many members of the conference. But I think it's interesting that there's this connection with Arithmetic-Geometric. So now I want to go to the last topic, and it looks like despite saying go slowly here, I've been talking a little too quickly. So that's good for you. That means I'll get to go this last part slowly. I'm not sure it'll help, but at least it won't hurt. Chilies will eventually show up. I'll try to keep them away as long as I can. So earlier, I sort of deliberately showed that this polynomial was non-negative by writing it as a sum of squares of polynomials. I wasn't lucky to be able to do this. In fact, you can show that if you have a polynomial whose degree is 2, you can always write it as a sum of squares if it is non-negative. And there's even an algorithm to do it. Those are, again, in linear algebra, the term is positive semi-definite quadratic forms for the experts. Now here's a nice picture of David Hilbert. I had this picture in my office when I was a graduate student until I took it down because I thought he was looking at me and was really disappointed. It was just hard to go into my office every day and see this guy looking at me. But he was a great mathematician. I'm not trying to do that. Well, maybe he would be disappointed in me. I don't know. So he proved an amazing thing, and he was only 26 when he proved that there exists a polynomial that is non-negative that cannot be written as a sum of squares. And this ultimately led to Hilbert's 17th problem in the year 1900. He gave a list of 23 problems that he thought would attract the attention of mathematicians throughout the 20th century. I was a mathematician in the 20th century, you can sort of tell by the gray hair, and I spent a lot of time thinking about Hilbert's 17th problem. Now the funny thing, and this is, I can't quite understand this, Hilbert said how you could find P, but he didn't write it down. And he didn't even give a very specific way of finding it. Or he gave a specific way of finding it that would be computationally impossible to work out in detail. And as far as I know, it took almost 80 years for somebody to actually work it out in detail. And what makes the story so nice is that when they worked it out in detail, it was a lot easier than Hilbert said it would be. And it involves the Arithmetic-Geometric inequality. So before I go any further, I'd like to pretend that I'm an applied mathematician for a little bit. Why do people care about this? Well, in part because the question of whether a polynomial is non-negative is very important to anybody who applies mathematics. Basically, if P is greater than or equal to Q, that's the same thing as saying P minus Q is greater than or equal to 0. There are books of thousands of combined pages listing inequalities that are useful in mathematics and applied mathematics. And it's not enough to say, well, I think it's positive. You need to be able to give what's called a certificate that something is positive, which is an assertion that is a verifiable assertion that it's true. You might think that it's enough to check a polynomial at 1 million random values. And in fact, with Mathematica, you can check at 1 million random values in a minute or two. And Mathematica will tell you the smallest value of the polynomial of those 1 million random values. And you think that if that was always positive, you'd have a pretty good sense that the polynomial is positive. But the problem, there's a problem with scale, especially when there are a lot of variables. Suppose you have a polynomial in 20 variables. Now, you don't see these in school, but you see these in practice. Let's say you wanted to check the value of your polynomial where you give each possible choice of 0 and 1. There are 2 to the 20 choices. That's more than 1 million right there, and you haven't even put in negative values. And if you knew that the polynomial was positive just of these 2 to the 20 values, you wouldn't necessarily be convinced that you had a really positive polynomial. And what happens is that the actual determination of whether a polynomial is positive is a very hard problem. Ask your local computer scientist just how hard. I think it's indeed hard. I'm not. I didn't know that would be on the test. I'm sorry. I don't know the answer to that. It's a very hard problem. On the other hand, determining whether a polynomial is a sum of squares is an extremely easy problem, at least for a computer. It's in a class of problems that's called semi-definite programming. And you can decide very quickly if a polynomial is a sum of squares. So if you're lucky, if you can write P as a sum of squares, you have a quick answer to a problem that in general would be very hard. So about 15 years ago, I suddenly started getting communications from engineers and applied mathematicians who were really interested that I was interested in polynomials that might not be a sum of squares. And it would take me too far in a public lecture to go into that, but let me mention that even if P isn't a sum of squares, if you happen to write P as a quotient of 2 terms, and you know both of them are positive, then you know P is going to be positive. So, to be a little technical, the game is to find good denominators for a polynomial so that when you multiply it, you get a sum of squares. Theorem Motts Copolymer, not as famous a mathematician as David Hilbert, but an extremely interesting mathematician. In the early 60s, he organized a seminar at UCLA on different proofs of the AGI. So it's not just me who likes different proofs of the AGI. I actually, my first year at Illinois, somebody organized a seminar and there were 30 different proofs that about 10 different people been presented. If you know more math, you can find a lot more proofs than what I've talked about today. In the course of his work, he discovered a remarkable example which was published in 1867. This is called the Motts Copolymer. Now, if you're interested in mathematical history, it becomes a philosophical question. If I say this is the first example, how do I know this is the first example? Because I wasn't alive every year from 1888 to 1967, despite appearance. Well, there's actually a human connection between the two. Olga Towsky, who was a great 20th century mathematician, was Hilbert's final assistant. And Olga Towsky loved sums of squares. I think it is fair to say that if anybody had found an example of Hilbert's criterion while Hilbert was alive, they would have told him about it. They would be hoping to have the great man come and maybe pat him on the head or something. That didn't happen. Olga told me that she had been watching continually for examples like this. She happened to be at a conference that Motts gave a presentation of this. If you want something strange, the conference was at the Wright-Patterson Air Force Base in Dayton, Ohio, and it was on inequalities. And Motzkin didn't realize that his example was the first one that had ever been found, and Olga Towsky told him. So that's how I know, and I'm pretty confident in making the statement that this is the first one. So here's how you prove it. We're already up to 2 here. If you take the Motts polynomial and divide it by 3, it's written as an arithmetic mean, and if you do a little bit of figure, can't figure this out. You've got this right-hand side is the geometric mean of the terms that appear. So you know that n is positive. The last thing I'm going to present, and I think it'll be okay on time here, is an explanation of why the Motts polynomial is not a sum of squares of polynomials. I say this is the easy part. This actually requires some proof, but it's too late for me to give a proof. I didn't write it up. You wouldn't be interested in it anyway. M has degree 6. Each of the monomials is degree 6. So if it's a sum of squares, each of the squares has to have degree 3. On the next page, I'm going to write polynomial of degree 3 in a weird way. X cubed, x squared, y, x squared, z, and so on. Now the way I'm writing this is that x to the I, y to the j, whatever the power of c is, gets put at the place whose Cartesian place is ij. So this is 2 units over and 1 unit up, so it's x squared y. And I'm going to write m in the same way. So what's the coefficient of y to the 6th in this sum? There's nothing that cancels with y to the 6th. You only get am squared. What's the coefficient of y to the 6th in here? Trick question. It isn't in there. What does that mean? That means its coefficient is 0. So 0 is a summation of am squared. And because the am's are real numbers, each of the am's has to be 0. So am is gone. Now, you can do the same sort of argument in the way of saying that you lose this, this, and this, and you lose this, this, and this, because there are very few terms in the Motts polynomial. Now, I'm sort of waving my hands, but with an hour, I could persuade a mathematician that this is true. But I think you all want to have dinner, so. This is what the terms look like. The terms that were left were z cubed, x squared y, xy squared, and xyz. Those are the ones I didn't cancel. And notice that it's the same shape as the terms that are in the Motts polynomial. That's actually something that you can do. Lots of people do. So in the end, we've got this expression. This is the Motts polynomial. This is what's left of the squares. Now, one more thing. I want to look at the coefficient of x squared, y squared, z squared. Over here, it's -3. Here, the only way to get x squared, y squared, z squared is by taking em squared, because the other terms that would multiply to x squared, y squared, z squared, one of the coefficients was 0. So you get that minus 3 is a summation of en squared. And this is a contradiction, because the sum of squares can't be negative. I said that earlier on. This is actually Motts original proof. Now, some of you may be familiar with Paul Erdős, who was a great mathematician of the 20th century. And although he was not a very religious person, he used to say that God kept a book of the best proofs of mathematical results. Ultimately, the smoothest, the ones that are the most insightful. And if he liked a proof, he said the proof was in the book. This proof is in the book. There actually is a book called Proofs from the Book, and this proof is in that book. That's it. And what's astonishing is that this was the very first proof in the modern study. It's written in mathematics, usually the people who make the breakthroughs, the proofs aren't very pretty or short. But Motts found this as the very first proof. So this is the last mathematical thing I want to present. I do want to say a little bit about the title of my talk. It is upon, especially those of you who are familiar with Raymond Chandler, who wrote in the 1940s, Philip Marlowe, his great detective. He wrote about Philip Marlowe. Down these mean streets a man must go who is not himself mean, who is not tarnished or afraid. And in preparing for this talk, I discovered this picture of Humphrey Bogart as Philip Marlowe in The Big Sleep from 1946, which is pretty soon after he wrote this. Notice that Humphrey Bogart is standing underneath the engineering work section on the bookstore. It's almost as if this picture was taken so that somebody would be using it in a math class, in a math lecture, 60 some odd years later. So, that was my last slide. I want to thank you for your attention, for coming.
Well, thank you for a very interesting talk. Now, I think we have some time for questions. Any questions? Comments?
So this example, the triangle that points in the exponents of the Motts polynomial, more complicated examples fit into exactly the points in edge region and so on.
The general theorem, and this was actually in the first paper I wrote on the subject in 1978, so I'm very happy you asked me this question, is you look at the monomials in P, look at the polytope, forget me, non-mathematicians, you look at the polytope whose vertices are the monomials of that polynomial, take that polytope divided by 2, and those are the interior points are the only ones that can occur in any sum of squares. So that does generalize, and it's also true that if you have a positive polynomial, the extreme points are even. And, well, I could go on, but this is real, that it wouldn't be a public lecture. I did not know that was called the Newton polytope at the time. I called it the cage.
Bruce, you mentioned you gave a couple proofs, and in some of them it was easier to see than others that you get the maximum value when all the numbers are equal. So
Yeah.
I can see that in the geometric one. You need a little more with the simple algebraic one. You need a little more work.
Well, what you need to do is every time you make a substitution, you have to look at when the substitution gives you equality. So here. No, I think it's the one just before this. back, stop. Okay, to go from here to here, this is only equal if x is equal to y. This is only equal if z is equal to w. So in the next step, this is only equal if the square root of xy equals the square root of zw, but the square root of xy is going to be x, and the square root of zw is going to be z. So this is now only equal when x is equal to z, and all three of them combine to get 1. And that's really all you have to do with other elaborations on that. And in this one, if you have equality, then here x and y and z have to equal the cube root of x, y, z, and then that goes back to x equals y equals z. Next. Okay, well then I guess you're all ready for the quiz. No. But I always wanted to say that.
Okay, so if you notice the very last sentence of the biography, Professor Reznick's biography says that during his spare time he likes to work on math problems. So actually when I read that part, I was wondering what does he do during his non-spare time? Presumably skiing. Anyway, so before we end this talk, we'd like to present to Bruce a total appreciation. Thank you for it's a mark.
Oh, thank you very much.
Thank you. I hope you enjoy the rest of this day.
Thank you very much. It is indeed a month.
Please join me.